Let's go into the chapter 2 of the niniBUS series. Okay. So we have discussed few things in the last chapter, right? So what we learned, this niniBUS is a data structure. It's just a simple data structure at this moment. Okay. It's a loosely data structure. I will not tell it's a data structure like a map or something. It's just a loosely coupled thing. I'm just trying to tell it. It has some functionality. Okay. So till the time we have discussed a few things, I want to reiterate one more thing. We are not implementing multiple producer, multiple consumer, thread synchronization, process synchronization, all those things at this moment. We want to make it boring and concrete for a single process or a single threaded application. Okay, we'll make the data structure as concrete as possible, then slowly we will move into different directions of implementation, right? Or different use cases. Okay. So what we learned, that we have a data structure and we have a producer and we have a consumer. All right. Producer put into the data structure, and the consumer poll it one by one, right? The ideal situation will be you produce something and at the same moment the consumer consume it, poll it, right? How beautiful things will be, right? One application produced, another application come and consume. But it's not going to be the case, right? Maybe the consumer is slow, right? And producer is fast. Producers trying to produce quickly and put into the queue. And consumer sleeping, came once, read one data, left. Producer tick 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 tick, forced data he post. Consumer came, read one data, left. And what happening? My queue is increasing, my data structure is increasing, size is increasing, right? Now it's a problem, right? I have to maintain a bigger queue, much bigger, slowly. Uh, let's, as we discussed, right? Also, the idea of the niniBUS is make it simple, and basically the use cases is around the embedded or IoT devices, right? That is the use cases we are planning, right? We are not going to a big server, cloud, and all those things. No, a simple embedded devices or IoT devices. I have a niniBUS data structure. So in that case, memory is scary. We don't have the privilege to have everything. No, we can't have, right? We cannot have all the memories. I cannot grow beyond some certain extent, right? I have to do something. Either I have to stop the producer, or either I have to make the consumer so fast. And in both the cases, I don't have the control. I don't know what the producer or what the application going to do, when to read, when to write. I don't have any control. And I have a constraint. I cannot go beyond certain extent, right? I have maybe a memory of few bytes or few MBs. I cannot go beyond. Now, right? So when you take the data structure, let I am giving you some size of 10 bytes. Let, like, every lane you can have maximum 10 slots, right? In a queue, my lane is a 10 slot. That means 10 messages you can put. That's, I am just putting a constraint at this moment. This can be changed, right? Like user can give more memory to the bus or the little lanes, right? That we can do later, but put it at the moment. I have a bounded buffer, right? That's it, right? Correct. I have the bounded buffer. Okay, my bound can change to 10 slots to 20 to 30 slots later on. We can see where how to do it, how to use it. But at the moment I have kept a default value of 10. Okay, a LAN can have 10 messages. A LAN is a for a single LAN we can have multiple producer, but the LAN ID is same, right? For a single LAN ID I have 10 slots I've given, right? That is bounded. My buffer is bounded. That's how it actually works in the embedded. You cannot have all the memories, right? You have constraint. So I can give you some small memory to run, and that's fine for us. Okay, we'll manage. So now the problem is that what to do if I have a 10 slot producer producing 10 datas. Our consumer is still not there. Our LAN is full. The idea is, yeah, that's okay. I have nothing to do. I cannot store everything. So I will tell you once you publish data, I don't have a slot. I will tell you LAN is full. That's a good design. Fine. Now think something. If I give the application, the producer, a little bit more power, little bit more privilege about my data structure. When you produce, I will tell you how much credits you have. Credit means loosely to the slots. How many slots still you have. That means if I have a 10 slots and you produced one data, I should reply you back, okay, my producer produced, okay, result is okay. Plus, I am giving you an extra information that you have 9 slots available. That's for the credit. The LAN credit, the LAN have 9 credit till now. Producer come again, put a data. He got, okay, result is okay, 8. That means, okay, I have 8 slots now. That's good, right? What will happen in this scenario? Producer have the power that, okay, in the ideal scenario, I should have got if I put a data, like 10 slots, I put a data, I would get 9. And I'm expecting the consumer must have consumed it before I push the new data. So the producer put a new data and expecting the consumer already consumed it. He's expecting, okay, I will get 9 back, right? Because I have a slot size of 11 at 10. So I would get 9 back. But if we're getting little bit slow, by if we're getting 9, then 8, then 7, the LAN credit, that means the consumer is slow. Okay. And the producer can come to know, okay, I have credit is 8 is available. I can put 8 data more. So I can put 8 more data or 5 more data. But he has the idea now that what is the slots, how many slots are available. So similarly, it's kind of back pressure, right? I am just telling the producer, you manage the back pressure. Okay, you can slow down or you can be faster because you have more slots, you go faster. Less slot, slow down, slow down, slow down. Right, this is how a TCP flow control works, right? If you know in the TCP, every packet sent from the sender, receiver send an acknowledgement. It's not only the acknowledgement, receiver also send something called buffer size. I don't know exactly the terminology used there, but it sends a buffer size which tell the sender that, okay, receiver have this many buffers available, so I can send this many bytes. Okay. And if receiver send small bytes, that I have small buffer available, sender will be slow down. Big buffer, sender will exponentially send data, more data, right? And just one acknowledgement will send, okay, I have buffer is getting full, slow down. Producer will be like, the sender will be slow down. Okay, that's how I'm trying to design here. This concept is inspired from that instead of sending the LAN full message, okay, let's have one more variable called the LAN credit. So producer have this idea that how much LAN, how much slots available, so he can decide to go faster or slow down. That's a good design, right? So that's how I'm trying to design. So the niniBUS not going to handle the back pressure. Okay, it is telling the producer, you take the back pressure, you handle it because you know the application much better than me, right? That's good. Now come to the consumer side. Okay, consumer read the data. Okay, reply is okay, receive. Okay, but if I send something more, that if I send how many datas or how many slots are available to be read, Producer already produced and put it in the slot, but you are reading only one, but you have 4 things more to be read. I can tell consumer, you need to be faster now. You need to be faster. Because already producer is producing lot of data and you are not consuming. You can be faster. And producer you can be slower because consumer is not consuming. Okay. That's how the backpressure can be handled between producer and consumer. And my bus will be like, I am facilitating, I'm giving the privilege to know the number of data or slots available, or the number of data to be read, right? Okay, simple. Okay, so let's jump into the code and see, okay, how things looks like. Okay, here is the niniBUS h, right? It's include file. So I always trying to show you from the data structure point of view. I want to show you everything from the include files, right? The include files tells much more things about how we are managing the data and what is the return type, what you are trying. So if you see the publish, I am returning a publish result. Okay, and that's it. Let's go to see what is this publish result. Yeah, that's what I'm publishing the result. I'm telling you win 32 credit. That means I'm trying to tell, once you publish, I will tell you how much remaining buffer slots available for you and the status. If it is okay. If it is lane full, that means 0 credit. The credit should be 0. I should return you lane full and 0. If lane is not full, I will send you okay, and I will send you the remaining size available. Okay, that's how. Okay, at this moment I've implemented the publish side, the receiver side not yet implemented, but we will definitely going to implement. Okay, simple, right? Publish credit, and we can argue later on, do we want to put a structure, we want to put a class, we can have a single event 64 byte data, event 64 bits, like 64 bit data, we can send both together. This can be argued, right? That's fine, but I just want to show the architecture of it, like what my thinking process and how do I'm trying to design it. Like if you're trying to design it yourself, your way, that's okay. That's if you design also, right? That's okay. Now come to the so you publish the data and I return IT second push message. Oh, that's a big thing, right? Yeah, that's okay. So what we know, right? Once we publish the data with the lane ID, I am going to find the lane ID is available or not. Okay, lane ID is available or not. I want you to look into try emplace. So previous time when I saw the code, the try emplace was not there, but you should see. And I have from design decision marker file, which will tell why I have taken try emplace. Okay, it's nothing, but if the lane ID is not there, it will create for you, right? That's what we decided last time. The lazy lane creation. Lane ID is not present, I'll create it. Okay, but it present. It will return the IT. If it's not present also, it will return the IT after creating that one. So IT is my iterator over here. So IT is second. So if you know, this lane map have two things, right? A key is lane ID. The second part is the object of the lane, right? Lane ID and the object. So I got the second, IT second. So I got the object. I am trying to push my message. Let's go into the push. Auto definition. Okay, nice. Okay, let's stop here for a moment. Okay, let's go. So I am trying to, this is my queue, right? Content pushback. If it is a success, okay, I am able to push the data, right? I'm able to push the data. Get the credit, return okay. I'll go and show how the code looks like. Get the credit, return published, okay. If not, if it is full, success or full, right? Or fail. If it is full, credit, no credit available for you, and land is full. Simple, right? Okay, that's how it looks like, right? As simple as post the data, get the credit, return the credit. If lane is full, return 0 and lane full, right? That's how I designed. I want to go a little bit more about the lane type, right? So in the lane, so last time we have created one queue, DQ we have created mostly, right? We have created a DQ. So what I thought of, because it's a DQ and in STL from the C++, I don't have much more power now. Okay, I don't have. So what I tried to did is I created an, instead of DQ, I created one niniFIFO. It's a FIFO, fast in, fast out, like same thing as a queue. Go to definition. What do we have? Oh, that's beautiful. It's a queue, right? It's a queue. Okay. What I did, I have put the capacity, that is the bounded buffer size. What is the maximum size a lane can store? The lane have a queue and the queue have the bounded buffer, right? At this moment, I make it default, something 10. But slowly we are going to introduce how user can define this size, okay? And a vector, std vector, which is the actually how the data going to be stored, okay? At this moment I'm creating the vector, but slowly we are going to design our own allocator, our own something like some storage classes. At this moment I'm creating a vector. Why vector? Because vector is easy to manipulate, right? With the index we can go, we can do forward, backward. With the index we can access also, right? Then question is why not array? That's a valid question. But I'm just creating vector. It's because I don't know at runtime my capacity can change, right? Like, but the std array requires a compile time variable, right? So just little bit of future thinking, I just kept a vector, but we are going to change the vector also. Simple. Now you post the data, it's come to post back. Okay, let's see now. You post the message, right? So let's go to the post message here. Nothing is doing, it's sending post back, content.post back. Nothing is content post back. If it is full, if the queue is full, because I have a size or capacity, if it is full, return full. If not, put the data in the back, buffer tail, increase the tail size. And I'm calculating current size. Current size means I have a 10 slots. You put a data, so my current size is 1, right? And credit level is 9. If you remove the data, my current size is 0, right? That's how it works. Same thing in pop front. If empty, return empty. If not empty, read the data from the head in the queue, right? You put in the tail, read from the head, right? Put it, increment the head, return success, right? Simple as it is. Okay, we'll go through the data structure a little bit more maybe in the next video. But the main concept which I want to explain you today is the credit system, right? This is one new concept, at least for the niniBUS, right? It's a naive approach. Here I am trying to tell the producer and consumer or the application, you manage when to be faster, when to be slower, when to send data, when not to send data. I am just a simple data structure and I have this my limitation. I cannot go beyond it. I cannot have all the memory. I don't have that privilege. Saying that, it will help me something else also. In embedded, one thing is you need to tell and read and write should be determined. You need to tell that read is happening like at delta t time. It should be deterministic. Every time you do a read, it should be delta t time. It should not be go beyond or let's be slow down. That means it need to be deterministic, right? You cannot write and you cannot, for the first write it is very fast and the second write takes long time because you have a bigger queue, bigger map, okay? That's why the vector came into picture instead of queue, because I have an index now, I can directly go to the index. That's the reason, right? we need to be a little bit deterministic that okay, I put a data, I know it will come in delta t time. Okay, I read the data. That's how it designed. Okay. So yeah, so this is the length edit part I want to explain in this video. That's what we explained also, and I want to really go into the. I really want you to go into the detailed, uh, not detailed code, but just go into the data structure part. Like, so previously we have a queue, everything was managed here, and we moved on the queue to a different data structure. niniFIFO created and moved it, and we have a design decision marker file which will tell every design decision I have taken, the reason behind every decision, every single decision. If it is an std array or std vector, there is an entry that why I have taken vector, not an array, why I have taken try and place instead of iterate or find. All the decision what we have made, I am putting it here. Okay, so I'm not going to claim this is going to be fastest message queue, but I can claim that it is going to be a good learning thing, and okay, that's what we claim. So again, saying that the niniBUS is going to be every part we're going to implement as boring as it is possible, and but we'll make it concrete. What I'm claiming till today, it should work. That's what my design philosophy I'm following, right? Okay, that's it. Let's have fun next time. We will have something, another chapter we'll discuss. Till the time, take care.